continuously monitoring, but you take over. You have to introduce the title and the speaker.
Okay.
And maintain the timing. I'll be monitoring everything from my side also, but you take over after that. Okay,
okay sir. And sir, one more thing. My presentation is postponed, right? I heard.
Yes. We have kept that in the third day, and I asked the chair and co-chair of that session to make that presentation in that one.
The Indian satellite began with Aryabhatta, the first Indian satellite, from a simple spin-stabilized satellite in the low Earth orbit to the highly complex interplanetary missions. The evolution of the Indian satellites in the last 5 decades has been phenomenal and astonishing. Today, India is one of the pioneering countries to use satellites for its rapid overall development. It has been a challenging and interesting journey over the years, with an array of satellites for communication, meteorological, remote sensing, navigation, scientific satellites, and when it comes to rockets like SLV, ASLV, PSLV, GSLV, and GSLV Mark III. These satellites and rockets have been built by different ISRO centers. India has joined an elite space club by launching Mars Orbiter mission in 2013 and made India the first nation to succeed in its maiden attempt to reach Mars. Another feather in ISRO's cap was added when the constellation of 7 satellites created India's very own satellite navigation system. On February 15, 2017, ISRO created history and a world record by successfully launching 104 satellites on a single mission, PSLV C-37. On November 14, 2018, ISRO successfully launched GSAT-29 from Sriharikota. The satellite weighing at 3,423 kilograms, it was the heaviest satellite to be launched by GSLV from Sriharikota. Keeping with India's emergence as an economic and technological powerhouse, ISRO is now working towards manned flight. Many technologies were demonstrated as a precursor to the first manned mission. The experimental mission that paved the way for human spaceflight mission was the Space Capsule Recovery Experiment conducted in January 2007. After the successful launch of Chandrayaan-2 on board the Mark III M2, ISRO now boasts an operational heavy-lift launcher capable of putting a 10-ton spacecraft in lower Earth orbit. The maturity gained over the years in the launch vehicle area will be gleaned to engineer a human
scientist at NERL, and right now he has become scientist SF. And his main area of interest is aerosol cloud interaction. And to his credit, he has published many research articles, very interesting articles, and have high impact. And he also received several awards and is a life member of several institutions. And with this brief introduction, let me introduce him. And today he'll be talking on BASIS, a new observational technique to understand aerosol effects on clouds. Over to Dr. Ravikiran. Dr. Ravikiran, please share your screen.
So presentation is visible, sir?
No, please share your screen. Can you share your screen?
Ravikiran, we are not seeing your screen.
Is it visible, sir?
No.
Okay.
1 second, I am coming there.
Ravikiran, you are able to see the share button?
Can you share your screen?
Can you go to the open share tray and try to share the
Ravikiran, right hand side top, you have that share button. Share content.
Sharing problems, etc. Right. 1 second. Are you able to see?
No, not yet, sir.
Now?
No.
Is it okay?
No, we are unable to see.
Can you leave the meeting and join again, or can you?
1 second. Our people are coming.
What is this? Why are you doing this now? Close. Close this.
Share screen.
Yeah, yes, sir. Now it is perfect.
17 minutes.
Am I audible?
Perfect. You can proceed now.
Am I audible?
Yes, you are audible. You are very much audible.
Thank you. Sorry for the technical issue.
Ravikiran, your time is 17 minutes. Okay.
Okay.
Yeah, please.
Okay.
Yeah.
So first of all, I would like to thank N2+ for giving me the opportunity to present our recent research activity on aerosol cloud interactions. That is balloon-borne aerosol cloud interaction studies, a field campaign basis, basically meant for understanding and quantifying aerosol effects on clouds. I would also like to mention my collaborators, Professor Fujiwara from Hokkaido, Japan, Professor Rosenberg from TU Delft, Netherlands, and Dr. Wienhold from ETH, Switzerland, and NRL colleagues. As we all know, aerosol cloud interaction is a fundamental process which occurs at the microscopic level in the clouds during their lifetime with the influence of aerosol. And the aerosol cloud interaction as a process can be seen in multiple pathways. Like people have reported about different effects: cloud albedo effect, cloud lifetime effect, inverse cloud albedo effect, cloud immigration effect, and semi-direct effect, etc. And these effects are mainly intervened by the background meteorological conditions. So, for example, temperature, background temperatures, humidity, updrafts, turbulence, and determinant and entrainments, making it more complex. Not only to observe or verify, but in terms of observations, but also in terms of simulations also. Another important point is that these effects, aerosol cloud effects, they do not occur individually, whereas they occur simultaneously or linked to each other. That's what we call as cloud adjustments. Because of all these processes, it is very difficult to estimate overall effect of aerosol cloud interaction on radiation. As per the latest IPCC reports, the effective radiative forcing from aerosol cloud interaction is estimated to be -1 plus or minus 0.7 watt per meter square, with a variance, large variance from about minus 0.3 to minus 1.7 watt per meter square. This large variance is mainly because of limitations in the observations and complexity with the process itself. So when you look into the observations point of view, no single instrument or platform is to be sufficient either to capture or quantify the aerosol effect. So, for example, if you take the spaceborne or ground-based lidars, they are seriously hindered by the penetration losses. And if you take aircraft measurements or UAV measurements, they are somewhat reliable because they go close to the aerosol and cloud and they measure, but they're limited in terms of altitude and costly, and they cannot perform frequently. And therefore, multiple instruments with multiple platforms, either in situ or remote sensing, is the best approach that one can follow to understand aerosol cloud interactions. And with this in mind, we have started a campaign at NARL Gadanki named BASIS, Balloon-Borne Aerosol Cloud Interaction Studies, using balloon-borne in situ measurements along with spaceborne or ground-based instruments. And the observation approach follows as this. We will be launching our meteorological balloons, meteorological balloons with specialized sounders a few minutes before the Calypso satellite overpass during night time. And also will be operating ground-based lidar such as microbulbs lidar or ceilometer and my lidar from the Gadanki a few hours before, during, and after the balloon launch duration. And overall, altogether, this gives us the information on aerosol cloud on a profile. And the key aspect here is that the balloon can penetrate through the cloud, providing the aerosol information right below the cloud, above the cloud, as well as the cloud information within the cloud. So this cannot be possible either with spaceborne or ground-based lidars. So apart from this, we do operate ground-based radars from NARL. They are MST radar or lower atmospheric wind profile radar, and also the microwave radiometer, and also do measure the aerosol surface aerosol properties. The table shows the list of instruments which are supposed to be operated during a BASIS campaign. And if you see the first three instruments, Calypso, microbulbs lidar, or ceilometer, and my lidar, they are used basically to measure the total attenuated backscatter from aerosols and clouds. And the specialized balloon sounders, Cobalt and CPS, which are shown in the image here, which is taken during one of the campaigns. This is called the CPS sonde. CPS stands for Cloud Particle Sensor, and the compatible radio sonde. And this is called the Cobalt sonde, and this compatible radio sonde. Cobalt stands for compact optical backscatter aerosol detector. Cobalt provides the backscatter ratio from aerosol and cloud, whereas the CPS provides the cloud particle concentration and the phase of the cloud. And these radars provide vertical wind information, particularly the wind information, all the components of the wind, particularly the vertical winds. And the microwave radiometer, they provide the temperature and humidity profiles, and also importantly, liquid water content of cloud can be calculated using microwave radiometer. And then surface aerosol measurements can be obtained from climate observatory, which is operational around the clock. Information from aerosol, cloud, and background meteorological conditions obtained from these multiple instruments are able to understand the aerosol cloud interactions in the BASIS campaign. You see these in these campaigns, Cobalt and CPS are the specialized combination of Cobalt and CPS specialized sondes are used first time. So consistency in the balloon-borne measurements is assessed quantitatively using the both ground-based and space-borne lidar instruments. The data shown here in this slide is from first BASIS campaign held on 6th June 2017. The right side panel shows the profiles of data from Cobalt, that is at 450 nanometer, 940 nanometer channel backscatter ratio shown in blue and red colors. And then cloud particle concentration is shown as a, from CPS is shown as a block dots. And then average range corrected signal, average range corrected signal from the lidars is also shown as a profile here. Orange color is from the microbulbs lidar, and green magenta color is from the my lidar, and green color is from the Calypso lidar. So once the balloons are launched from the Gadanki, they drift away from the location because of the background wind conditions. So in order to collocate the balloon measurement, we have also plotted the temporal evolution of the surface-based lidar measurements that is shown in the left side panel. The bottom is the contour of range-corrected signal from the microbulbs lidar, and the middle panel is the contour of range-corrected signal for the same, but from the my lidar. And the top panel shows the total attenuated backscatter signal as a function of longitude from the calypso when the calypso was close to the launch station. And from the data, we can see that the cobalt, from the cobalt backscatter, we can see that it could able to see clearly observe the features, lower atmospheric features, especially at 4 kilometers. There is a significant peak, and at 9 kilometers another peak is there, and between 12 and 17 kilometers the multiple layers are there. At the same altitude, cloud particle sensor has also detected the particle concentrations, and similarly both lidars, same lidars also have seen shown these features at the same altitudes. However, if you see the lower tropospheric features are not prominent in the my lidar and calypso. On the contrary, upper tropospheric features are not prominent in the micropulse lidar. These things are mainly because of the penetration issues with the ground-based and spaceborne lidars. Coming to the 9 kilometer peak shown in the red channel here, this is not clearly seen in the profiles from the my lidar, but they are seen, but a little at lower altitudes. And if we collocate this data with the ground-based measurements, when the balloon was at 9 kilometer, it actually corresponds to the time of 2:45 local time. At 2:45 local time, ground-based lidars could not show any features. It was noticed in the balloon-borne measurements. It indicates that balloon has detected an independent either cloud layer or aerosol layer. But when the balloon was at 12 to 17 kilometers, the time was between 3 and 3:30 local time, early morning. Both the ground-based lidars has nicely picked up the features which are seen both in the ground-based and balloon measurements. Even though the balloon was about 30 to 50 kilometers away, when it was at 12 kilometers, the features are same. This is mainly because the launch was held during monsoon season, the June. In monsoon season, we have total tropical easterly jet, a characteristic feature of monsoon, where easterly jets with about 50 meters per second wind, and they sweep out the anvils of the deep convective cloud several hundred meters away. Because of this reason, even though 50 kilometers apart, both the ground-based lidars as well as the balloon has noticed the same features. And we have also looked into the data from another second basis campaign, and we conclude that the balloon-borne measurements are in good agreement with the ground-based and spaceborne lidar measurements. Apart from that, we see that they are giving some additional information compared to the lidars. The main objective of the basis campaign is to understand and quantify the aerosol cloud interactions. So for that, in a balloon profile, it is very much required to first separate aerosol and cloud. So earlier studies using cobalt, they have applied threshold conditions on the cobalt data, and they could able to separate aerosols from clouds in the upper tropospheric regions, in the atoll regions. But here the advantage is that we have a CPS sonde which can directly detect the cloud layers, and corresponding to these cloud layers, we can have the cobalt information, and the rest of the cobalt information can represent the aerosol. So the data shown here is from basis campaign held on 27th June 2019, and the first panel shows the temperature profiles and relative humidity profiles, and the second panel backscatter ratio from cobalt, and third and fourth panel number concentration and degree of polarization from the CPS. If you see here, there is a saturation just below 4 kilometers to 6 kilometers. This indicates that there should be a cloud, and cloud particle sensor has detected cloud corresponding to the same altitude. There are multiple cloud layers are there, and the degree of polarization is between 0.6 and 1. As per the details given in Fujiwara et al., if the DOP values are between 0.6 and 1, they correspond to liquid clouds, and these are the liquid cloud layers. But the top liquid cloud layer, if you note that, if you see the temperatures, it is the cold temperatures. So this may be a super cool liquid. And apart from this, the relative humidities are more than saturations, again from just above 8 kilometers to 11 kilometers. Again, multiple cloud layers are detected in the CPS, and this layer with the DOP between 0.6 and 1 is again a super cooled liquid cloud. And above that, we can see the DOP values are ranging between -1 and 1. From Fujiwara et al., this corresponds to as clouds. So in this manner, the combination of CPS and cobalt can be used to straight away separate the clouds and the aerosols in a balloon profile. So particularly, we have looked into the ice clouds information from both these sondes. The top panel shows the data from the CPS. So the particle concentration for ice clouds, it peaks at 0.1 to 1 particles per cubic centimeter, and DOP ranges between minus and 1. And if you see the backscatter ratio from cobalt, at blue wavelength it is between 1 and 10, at red wavelength it is between 10 and 100, and color index is between 1 and 10, 10 and 20. So these basis campaigns, we have conducted so many basis campaigns, and so far 15 campaigns balloons have been launched, and we have about from 8 launches we have ice clouds detected, and the cobalt color index for these ice clouds is plotted as a box plot shown in the left panel, and it is plotted as a histogram shown in the right panel. Different colors indicate the different campaign index. If you see that the color index of cobalt for ice clouds is between 15 and 25, 90% of percentile of the points are between 15 and 25, and mean and median values are around 20. So from these statistics, it can be concluded that cobalt color index of between 18 and 20 can be representative of a ice cloud. Since we have separated clouds and aerosols in a balloon profile using the combination of cobalt and CPS sondes, now it is our objective is to determine the or estimate the aerosol cloud interaction. For that purpose, we have developed a small scheme which actually looks into each and every balloon profile. It works only for liquid clouds, because in liquid clouds the aerosol cloud interactions are very much can be seen clearly and also reported very well. So top panel shows the actual data from one of the campaigns, that is a CPS particle count, concentration, and degree of polarization, and this is the cobalt blue color backscatter ratio. So as per the scheme, we first carefully detect the cobalt cloud layers, and then aerosol layers. The cobalt cloud layers are detected based on the following condition. If the CPS count is greater than 10, number concentration greater than 10 raised to minus 3, DOP greater than 0.6, relativity greater than 95, and temperature greater than 0, they are considered as the cloud. So we have detected a cloud just about 2 kilometers, as shown here. And now the aerosol is the below the cloud. So usually when we consider the aerosol below the cloud, it is important that there should be humidity influence that needs to be removed. So for that purpose, what we have done is the cobalt blue backscatter ratio is only considered, and it is subtracted from 1 to get the particle blue backscatter ratio. And then this particle blue backscatter ratio is ignored above threshold values of 3.1 to avoid the high values. And then we have again, apart from this, we have looked into the linear relation between the cobalt blue backscatter ratios below the cloud with relative humidity. If at all there is any linear relation, we have corrected the data so that we got the blue particle backscatter ratio, dry, we would say dry blue particle backscatter ratio. And then this scheme is applied to the all the basis launches from the basis campaign, that is about 15 campaigns, and we could found that among 15 we could found 6 campaigns liquid clouds are present, and the average median value of cloud particle count from the cloud layer and the corresponding blue backscatter ratio is plotted in a log-log plot as shown here. The blue backscatter ratio from cloud base to 300 meters, 400 meters, as well as 500 meters is shown in different colors. So this log-log plot, linear fit is done to this log-log plot, the slope of which indicates the aerosol cloud interaction index. And we have found that the index is between, it is 0.77 when you take aerosol from cloud base to 300 meters and 0.86 from cloud base to 400 meters, but it has come down when you consider cloud base to 500 meters, 0.67. So this indicates that whenever we are considering aerosol below the cloud, it should be up to 400 meters, not beyond that. And another point is that
Dr. Ravikiran,
yes.
Try to finish in 1 minute so that we will have 2 minutes for interaction.
Last slide.
Thank you.
So the theoretical estimates of aerosol cloud interaction shown here are well within the the estimates of aerosol cloud interaction shown here are well within the theoretical values of 0 and 1. To summarize, so we have adapted new techniques to understand and quantify aerosol cloud interaction, namely basis campaigns, so successfully conducted from Gadenki. And the first time combination of specialized sondes were used. The consistency of balloon measurements is found, assessed with the and compared to ground-based and spaceborne ground lidars, balloon measurements are giving added information. And this sound information in a profile can be used to easily separate aerosol and cloud. And then we developed a scheme to carefully identify the cloud layers and aerosol layers in a balloon profile. And then with this, we estimated the aerosol cloud interaction, which is found to be 0.7 within the limits of the theoretical values. And however, we could not able to constrain the meteorological background meteorological conditions, which is very important, mainly because we could not have more number of balloon soundings, and it is our next activity is to conduct more and more campaigns to get more number of soundings, so that meteorological conditions can be constrained and robust statistics of aerosol cloud interaction index can be estimated. So apart from this, we also have another approach of addressing this aerosol cloud interaction. That is another phase of aerosol cloud interaction effects. That is the cloud invigoration effect. So part of this, we want to make the measurements of synergy of cloud-based instruments like ceilometer, microwave radiometer, and cloud radar from relatively polluted location Kolkata. So these instruments are already, ceilometer is already deployed at Kolkata. So the main objective is to operate around the clock. These instruments will be operated so that aerosol, cloud, and background conditions relevant for cloud invigoration effect can be measured and investigated. Thank you. I'll end my presentation here. Thank you for your kind.
Okay, thank you, Dr. Ravi Kiran, for your nice talk.
Yes.
Now
Yes.
we can make this talk for open discussion. I request
Yes.
participants, if you have any need any clarification, please unmute your mic.
Kumar.
And, sir.
Lakshmi Kumar.
Yeah,
There
yeah.
are no posts right now in the comment box.
Okay.
And I think since it is already exceeded time, I think we will move to the next talk.
Yeah, okay, sir.
Yeah, can you please proceed?
Yeah, yeah. So we have we'll have talk now by the speaker Ajit TC. He's from SpaceX Laboratory. He is going to talk on role of aerosol microphysical properties on CCN activity over a tropical coastal station. May I know Ajit is present?
Oh, yes, sir.
Yeah, Ajit, please share your screen. Your time is 8 minutes. Okay.
Okay.
So 8 minutes. I will remind you. You have to stop the presentation by 8th minute. Okay, at the end of the 8th minute. Please proceed. Thank you.
Okay, good evening all. Myself Ajit TC from SPL. My topic of presentation is role of aerosol microphysical properties on CCN activity over a tropical coastal location. We know that aerosol impact climate by two ways. First one is direct effect and second one is indirect effect. Most of the uncertainty exists in estimating the indirect effect of aerosol or the aerosol cloud interactions. The cloud nucleating property of an aerosol depends on its size, chemical composition, and mixing state. The studies exploring the influence of these parameters on CCN activation is less, especially over coastal locations where the site receives contrasting air mass within a day. So regarding this, our objective is to delineate the role of aerosol size, chemical composition, and mixing state on CCN activation under contrasting air mass condition within a day. So on this backdrop, observations on the aerosol microphysical properties were carried out from a tropical coastal location, Tumba. The location figure is shown on the right side. So the observation period is from winter, January-February 2019. So during this period, the site receives continental outflow from the IGP region, and the instruments such as cloud condensation nuclei counter, aerosol chemical speciation monitor, which is basically a mass spectrometer, and scanning mobility particle sizer were operated. The methodology followed is Kappa-Kohler theory and estimating the CCN concentration. Being a coastal location, the site experienced considerable mesoscale circulation. The right side top figure shows the diurnal variation of the sea breeze component. So we can see that during the daytime, the sea breeze component is relatively very strong. So which brings clear marine air mass, cleaner marine air mass to the site. But during land breeze time, during night time, it is relatively polluted. So based on the sea breeze and land breeze, we have averaged the measured aerosol parameters, and the figure is shown on the left side. So from this figure, the red line indicates the CCN activation spectrum during the land breeze time, and the black line represents the CCN activation spectrum for the land breeze. So During sea breeze, it is seen that the spectrum is flat, which means that less supersaturation is required for the aerosol particle to get activated. So, which means the system is more CCN active. But during during this land breeze time, the system is CCN less CCN active, which means more supersaturation is required for getting activated. So the corresponding chemical composition and number size distribution also shown. So which shows that during the land breeze time, almost 80% of organics is present, whereas during the sea breeze, it is 40% inorganics are present. So we know that organics are inorganics are different much in terms of their hygroscopicity. So we can say that the chemical composition between sea breeze and land breeze is contrasting. But the same is not seen in the number size distribution, which is shown in the sub window. So only 10 nanometer difference is seen between sea breeze and land breeze. In the literature, it is widely reported that the CCN activity is mostly controlled by the number size distribution only, and less influence is given to the, or less importance is given to the chemical composition. But here we see that there is a contrasting chemical composition with the contrasting CCN activity, but this is not seen in the number size distribution. So we will be evaluating this aspect based on the Kappa-Euler theory. So based on Kappa-Euler theory, I have estimated the CCN number concentration using the real-time chemical composition number size distribution from the measurements. So this figure shows the number concentration of CCN estimated versus the measured. So we can see that the CCN estimation is less sensitive to the mixing state assumption. So for both internal and external mixing state assumption, the slope is almost near to 1, which means that the prediction is accurate. But for fixed chemical composition, especially for the land breeze time, fixed chemical composition means I have taken the average chemical composition and the chemistry is fixed. So during land breeze time, when the organic contribution is more than 80%, the slope is deviating or the uncertainty level is very high, which means that the knowledge of real-time chemical composition is essential for the better CCN estimation when the organic contribution is very high. So we know that in the atmosphere, organics evolve. It interacts with several oxidants and results in the oxidation results in the change in hygroscopicity. To evaluate how the hygroscopicity responds to the CCN activation, so I did a sensitivity analysis. I changed the hygroscopicity parameter of the organics. So we can see that for during land breeze time, the organics have a hygroscopicity of 0.05, which correspond to hydrophobic nature. So we have got two type of organics. One is hydrophobic organics during the night time or the land breeze time, and relatively hygroscopic organics during the sea breeze time. So the right side figure shows the triangular plot, which represents the oxidation degree of the organics. As we move towards the y-axis, the oxidation degree increases. So which means that during sea breeze time, the color represents the CCN activation ratio at 0.40 supersaturation, representing the convective cloud conditions. So during sea breeze time, the points are clustered on the top side of the triangle, which means it is highly oxidized with the more CCN activity. And during land breeze, it is clustered on the lower side of the triangle, indicating that it is less oxidized and less CCN active. So we have an indication like the organics are influencing the CCN activity. To further understand, so far we haven't fixed the size distribution. So for this, I have selected the similar size distribution. I have got 4 type of distribution. The idea is like within each distribution, the mode diameter is same. So the variability in CCN activation ratio shown on the right side, it only arises due to the change in chemical composition. So we can see that the variability in CCN activation ratio is high for mode 83 and mode 83 nanometer and mode 99 nanometer. So the number of distributions are also high in this mode. So which means that at a fixed size distribution also there is a large variability which arises due to only the chemical composition change. So to further see the effect of organics on the fixed chemical composition, the triangle plot is shown, especially for this lower bottom side for mode 99 nanometer particles, where most of the particles exist in this mode. We can see a clear dependence on the organics hygroscopicity or organics oxidation with the CCN activation. The color represents the CCN activation ratio at 0.40. So we can see as the organics are becoming more oxidized, it is enhancing the CCN activation. But when it is clustered on the lower part, which means it is less oxidized, it is reducing the CCN activation. So our results indicates that we have to consider the influence of organics on the CCN activation while estimating the CCN number concentrations.
Ajit, please complete your presentation.
So the summary is listed below. A clear contrast in aerosol chemical composition and CCN activation is seen, but it is not reflected in size distribution. In an organics dominant environment, atmospheric evolution or the processing of organics plays a vital role in CCN activation compared to the mixing state. So thank you.
Thank you very much, Ajit. Now it is open for discussion. If anybody has needs clarification, please raise your hands and talk. Kindly
I think
yeah, there is no question in the chat box as well as nobody raised hands. So we will move on to the next presentation. So next presentation is by Kavita Patnaik. She is from National Atmospheric Research Laboratory, NARL Gadanki. She is going to talk on sensitivity of cloud condensation nuclei concentration to aerosol loading in column model. So may I know whether Kavita is present here?
yeah, she's there. She's talking from NARL PS1.
Yeah, please. Kavita, your time starts now. You have 8 minutes for talk. Okay. I will remind you at 5:10. You need to finish your presentation by 5:10. Thank you. Please proceed.
Is my presentation visible?
No, not yet. You open the file. We are seeing only the list of files.
Yeah,
You double click the file.
Yeah, I have opened.
No.
No. Can you close it and again open?
I think you have to share your screen.
I think you are sharing the wrong window.
You have to share your screen, not the window, when you are trying to open PDF.
There are several windows are there.
Kindly share your screen, not window, so that we will see your screen and you can project your PPT, whatever is PDF form and other form.
Is it visible?
No, sir. So you kindly open the PDF and share the screen.
Wait.
There are two options, screen and window. You open the click the option screen after opening PDF.
Is it okay now?
Yeah, now it is fine. Yes.
Make it full screen.
Kavita, please make use of your time, please.
Yeah. Good evening, all. I'm Kavita Patnaik. I'm going to present on sensitivity of cloud condensation nuclei concentration to aerosol loading in column model. It's a mathematical formulation, and we have performed some idealized experiments. As several discussions have been there about the aerosol vertical variation playing an important role in climate change processes, and its effects, direct effects and indirect effects have been discussed today. And the most important thing is the aerosol chemistry and its uncertainties. Those are not clearly understood till now. They are there is a challenge to represent these uncertainties in a model. So we have proposed a methodology in which we will be using Monte Carlo simulation by perturbing temperature data during an extreme rainfall event, so as to understand the change in concentration of chemical species with a time step of 1 second. So here I have represented a one-dimensional box model to which we are giving input as the aerosols, the chemical reactions and its rate of reactions, and the vertical profiles, that is the number concentration of aerosols, to our box model, and we will be solving using numerical techniques. So hence, so that we can study the impact on extreme precipitation. sets which we have used are the first, we have taken IMT rain gauge observations over Delhi for 35 years and we have calculated the mean. Here we can see that the orange line shows the mean of the rainfall data of these 35 years and the black dotted line is we have calculated the mean plus 3 cross standard deviation, which the points lying above this black dotted line, those are the extreme precipitation event days. So for those events only we have conducted this study. So and the second data set that we have taken is for initialization of our model. We have used satellite data, that is community long-term infrared microwave coupled atmospheric product system, the CLINCAPS. This is provided by NASA. They gave the vertical profile of gases such as water vapor, ozone, carbon monoxide, methane, nitrous oxide, nitric acid, sulfur dioxide on 100 fixed pressure layers. Here I have shown the retrieved profiles of the methane, carbon dioxide and ozone over Delhi for a particular extreme event day, that is 13th July 20th July 2013. Next, I will be discussing about the methodology that we have adopted. So for Monte Carlo simulation, basically we follow, it is a model used to predict the probability of different outcomes with the intervention of random variables to explain the impact of risk and uncertainty in prediction and forecasting model. It follows the algorithm, that is first we have to start the model, then we have to determine the statistical properties of model inputs, then we have to generate a random sample input, then we have to compute the model output and store the model output. Then we have to see whether the model output is matching with the observation, and if it is yes, then we will conduct the statistical analysis on that output, or else we have to again generate a random sample input and this loop follows. Next, I will be discussing about a statistical method, that is the maximum likelihood estimation. As I have said, that Monte Carlo simulation, we need a random set of sample input. So for that, this MLE follows 4 steps. That is, first we have to make a distribution assumption. Then we have to find the likelihood and the log likelihood of the function. Then we have to find the maxima by taking the derivative. And here I have shown a few random set samples of data of temperature generated at different pressure levels. The orange line shows the random values generated by using this statistical method, and the blue line shows the MLE fit. This data we have taken from radio sonde observation for 20 years for that particular day, extreme event day over Delhi, 20th July, and we have generated this random set of inputs of temperature data. Next, the gear solution. This is a method, numerical method used to solve backward uses backward differentiation formula to solve the for this numerical technique. And here we check the convergence by using local error test, and after completion of all iterations at each time step, we check the do the global error test. And this algorithm in the right side shows the this algorithm we have used for our study. For this gear solution, we have taken the IMT precipitation data, as I have shown, that from that we have identified the extreme precipitation days, and I have discussed about the satellite data that we have taken for the initialization of our one-dimensional box model, and we have taken the radius on the observation temperature data. As I have discussed, that we have taken this data for the sample random generation of sample input data, and these things will go as input to our gear solution, and upon that we will perform Monte Carlo simulations so as to study the aerosol vertical profile and the sensitivity of cloud condensation nuclei at cloud levels to aerosol loading.
Kavita, please try to complete your presentation.
Yeah, sure. Then the results here, the first figure shows that this is a chemical reaction, formation of ozone and its rate of reaction. Here I'm showing that how the temperature and the rate of reaction are dependent. And the next figures, they are showing that upon decreasing the time step, we are nearing to the accuracy of the data, accuracy of a ozone profile. So when the time step was 30 seconds, the peak was lying around 600 hectopascal of pressure level. When we have reduced the time step and when we have made it to 1 second, that peak has it went up, which is nearing to accuracy. Then next, the gear solution, we have discussed that we have to check the convergence of local error. These figures show the convergence of local errors at different levels of troposphere, that is the upper level, at the middle level and lower level. Here we can see that at all levels, upon iterations, the error is decreasing and it is converging to zero. Then
Kavita,
next,
you can show the last slide, please. Conclusion slide.
This is the last slide. So here we can see the profiles of other aerosols too, like methane and carbon monoxide. And I would like to conclude my presentation with a few key points that we have identified the extreme rainfall event by using the mean plus 3 standard deviation formula, and with using MLE, which is a statistical method. We have performed generated the random sample data for our Monte Carlo simulations and gear solution, and upon decreasing the time step, we can get the accurate results, and this model is able to simulate the vertical profile of concentration of gases. And thank you.
Thank you, Kavita, for your talk on Monte Carlo simulations. If any participant has a question, please ask.
Now there is a comment. What might be the reason for a large change in the scale and shape parameters at 10 hectopascal data in the MLM method? Do you have any answer, Kavita?
Can you repeat the question?
What might be the reason for a large change in scale and shape parameters at 10 hectopascal data in MLM method?
This maximum likelihood estimation method, this shape, actually this is the density, the y-axis is density. Where the density is more of this temperature data, that peak is more, and where the density is less, the peak is that data is less.
Okay, thank you very much.
Thank you,
Kavita. And we'll move to the next presentation. Actually, this is by our co-chair TV Lakshmi Kumar, but this talk is not falling apt in this session. So we moved this talk to the third day, session 2. And with this note, can we please move to the next talk, Lakshmi Kumar, Dr. Lakshmi Kumar?
Yes, sir. Thank you. So we'll have a talk now by Mansi Gupta. She's from Physical Research. Mansi Gupta is from Physical Research Laboratories. So the talk will be on variability in atmospheric DMS over the Bay of Bengal during the post-monsoon season. May I know Mansi Gupta is present? Mansi Gupta, are you here? Yeah, please share your screen. Yeah.
Is it visible, sir?
Yes.
Okay.
Please complete your presentation by 5:22.
Okay, sir.
No, Lakshmi Kumar, please mention the timing only, please, because they cannot see the timing in their screen.
Yeah.
You please mention at 8 minutes, so you please ask them a note.
Yeah, okay, sir. Okay.
Okay, sir. Shall I start now?
Yeah, please proceed.
Yes, please.
Hello, everyone. I'm Mansi Gupta, Junior Research Fellow from Space and Atmospheric Sciences Division, PRL, Ahmedabad. And I'm going to present on variability in atmospheric DMS over the Bay of Bengal during post-monsoon season. I'll start with the introduction and sources of DMS. So DMS, dimethyl sulfide, is the most abundant volatile organic sulfur compound present in remote marine atmosphere. It plays a major role in global surface sulfur cycle. It also accounts for almost 60% of natural sulfur gas emission into atmosphere at global level. And it is produced through biologically mediated processes, and mainly involving enzymatic lysis of DMSP, which is the osmolyte released by phytoplankton. And major processes of DMS release into atmosphere is air-sea exchange. Now this air-sea exchange depends on thermodynamical forces like disequilibrium of concentration of gas along either side of air-sea interface, or biological processes, since not all the phytoplankton species produce similar amount of DMSP under stress like zooplankton attack, virus infection, and temperature salinity change, basically environmental changes. And there are other physical parameters like wind turbulence, wind breaking, sea surface temperature, solar flux that are involved in the in controlling the AC exchange. To quantify AC exchange, the most popular thin film model is used. The flux is calculated using this formula, and Kw represents the transfer velocity, delta is the concentration gradient on either side of the interface. Here the concentration gradient can be calculated through this formula where I've written which variables are what. So now I move on to significance of DMS in terms of atmospheric chemistry and climate change. Oxidation of DMS, it leads to formation of secondary sulfate aerosols, and these aerosols, they grow to act as CCN and participate in cloud formation. So DMS directly or indirectly, it modulates Earth's radiation balance by interacting with solar radiation directly or through clouds. So DMS certainly represents one of the key linkages between biogeochemistry of ocean, marine aerosol formation and growth, and subsequent impact on climate, as illustrated by in Claw hypothesis by Charlson. Hence, in situ measurement-based studies of DMS are important in marine atmosphere to understand the chemistry-climate interaction at regional and global levels, and hence improving our atmospheric models. So we participated in a cruise campaign over Bay of Bengal in September-October 2021. And with respect, our objective was to study the spatio-temporal variation of atmospheric DMS and VOCs over Bay of Bengal during the post-monsoon season. In respect to DMS, we focused on studying the variability of DMS in marine air and its relation with meteorological parameter, as well as the roles of biological factors and AC exchange in detail. This is our study area. We started from Chennai, moved through the open ocean to Andaman Sea, and then back to Chennai through a sudden transit. We did continuous measurement of DMS using sulfur trace gas analyzer, consists of a gas chromatograph and flame photometric detector. These are some typical chromatograms, and the distinct peaks that we are seeing in both the ambient and calibration gas chromatograms is the DMS. We'll move on to results and discussion section. Here we have time series plots of DMS mixing ratios, few meteorological parameters, as well as latitude and longitude. So in the first plot, we have latitude and DMS mixing ratio towards left and longitude towards right. Here we can see that while moving from Chennai through the open ocean towards the Andaman Sea, there is not much variation in the DMS mixing ratios in the atmosphere. However, there is a sudden elevated mixing ratio, that there are sudden peaks observed in Andaman Sea. And again, for this, while moving back towards the return transect, there is not, like the changes is less compared to Andaman Sea. However, one more thing can be noted here, that for the similar longitudinal range, there we see less variation in DMS concentration for the northern latitudes than the there is more change, there's more variation in and higher concentration of DMS in the southern latitudes. Now the second plot, in the second plot we have air temperature, relative humidity and DMS mixing ratio, air temperature and DMS mixing ratio towards left and relative humidity towards right. Here we can see that the change in DMS mixing ratio, it follows comparatively well with the change in relative humidity over the region. Now, this can suggest one thing, that in many regions, the contribution to DMS concentration in the air is directly impacted by the release from the surface water below. However, there can be other factors influencing the surface in the atmospheric concentration, including maybe transport of air masses from another region, which could enhance the DMS concentration or dilute the air and decrease the concentration. Although in the third plot we have wind speed time series, although we do not see any distinct relation between DMS concentration and wind speed through this, but we are looking into it, since the wind speed is an important parameter that controls AC exchange. Further, we observed a mean mixing ratio of 0.38 plus minus 0.15 ppb over the open ocean, in open ocean over Bay of Bengal. And the reported range over the whole study period was 0.13 to 1.77 ppb. The previous studies have shown high range of variation in DMS concentration all over the world in open ocean, and it can depend on various factors like different environmental conditions and different climatic zones, probably which will be impacting productivity or the other factors that control the emission processes or the formation processes of DMS. A crucial study by Shenoy et al. Have reported DMS seawater concentration during intermonsoon season in Bay of Bengal. The figure here, it represents variation in sea surface DMS concentration in Indian Ocean. So we can see that as we observed in my result that for same longitudinal transect in open ocean, higher values for DMS were observed over southern latitudes. That is in the return transect. And from the study, we can relate that perhaps the increase in oceanic DMS concentration could account for the higher release of the gas in the atmosphere towards the south in Bay of Bengal. Or say it could be one of the reasons.
Try to complete your presentation.
Yes, sir, I'm almost done. So, or it could be one of the reasons among other factors. We are still studying, we are still looking into it to understand the air-sea exchange here over the region in detail, and to assess the relationships between DMS concentration in atmosphere and oceanic parameter using satellite data. To summarize my presentation now, so DMS is as we saw, DMS is the most abundant organosulfur compound present in marine atmosphere. It plays a major role in global sulfur cycle and is released in atmosphere primarily through air-sea exchange processes. And then we conducted a ship campaign in September-October 2021 to study spatial variation in DMS over Bay of Bengal and role of contributing factor. Our results show range of DMS concentration mixing ratios from 0.13 to 1.77 ppb, and with an average of 0.38 plus minus 0.15 ppb over open ocean. There were significantly elevated levels observed in Andaman Sea compared to open ocean, and the greater surface water DMS concentration were observed along the southern open ocean transect compared to northern transect. Could be an important factor explaining the higher DMS in air along the return transect. Our study provides the first in situ experiment of atmospheric DMS over the Bay of Bengal, and in there I would like to say that our results would be valuable for researchers working in chemistry climate interaction studies over the northern Indian Ocean. Thank you for your patience.
Thank you, Mansi, for the talk. So there are two questions. We will have some quick answers for these questions. One is from Dr. D.K. Deshmukh. So his question is, what is the major formation pathway of sulfate from DMS, gas or aqueous phase? You have
Sir, it's mostly the oxidation of DMS by radicals like hydroxyl radicals or halogen radicals in gas phase.
Okay, the second question is from Chaitanya Jain. He is from NARL. What is the lower detection limits of DMS measurements and uncertainty in GCFPD? How was DMS is sampled?
So can you please repeat?
What is the lower detection limits of DMS measurements and uncertainty in GCFPD? How was DMS is sampled?
So, sir, we took a real-time DMS, we did real-time DMS sampling. Our GC was continuously taking samples from air, and there was a cycle of 30 minutes. So in every 30 minutes, we have one chromatogram, and so that is what there is one value of DMS for every 30 minutes while the ship is moving.
Okay, thank you. We can have one more quick question. It's from Lakshmi here. She raised her hand. You have any question, yes, Lakshmi? Sir? Please. No.
Sorry. It was by mistake. Sorry.
Yeah, thank you. So thank you, Mansi, for your nice talk. Thank you very much. So now we will move on to next talk by Gopika Gupta. Gopika Gupta is from NARL. The talk will be on long-term trends in aerosol optical depth obtained using multi-satellite measurements. Gopika is here. Gopika, are you here?
Yes, she is there. She is there. She is from NARL PS1. She is presenting.
Yes, yes. Thank you. My Gopika, your talk is about 8 minutes and 2 minutes is left for discussion.
Gopika, can you share the screen?
Yes, sir. Sir, is it visible?
No, please share your screen.
No.
Yeah, it is not shared.
First, to open the PPT file.
I'm closing.
Okay.
Share. Now this one. Now this one.
Yeah, now it is good. Please put in. Yes, now it is perfect.
Okay, sir. Hello, everyone. My name is Gopika Gupta, and I'm currently.
You please project fully. Highlight. But full screen mode is not coming. Your slides are yes. Proceed.
Hello, everyone. My name is Gopika Gupta, and I'm currently working as SRF in NARL. The topic for my today's presentation is long-term trends in aerosol optical depth obtained across the globe using multi-satellite measurements. Firstly, I'd like to give a brief about my topic. So as we all know that aerosols have a net negative radiative forcing in the atmosphere, which counteracts the net positive radiative forcing induced by the greenhouse gases. One of the essential parameters to estimate radiative forcing is using the observation, which can include in situ and remote sensing observations. But according to IPCC report 2013, they have clearly mentioned that there still exists an uncertainty with the factor of 3 due to aerosol radiation interactions alone, which can arise due to the much uncertain emission sources of aerosols. So as we can see from this graph, that since 1850, there has been a huge variation in the different types of aerosols, whether increasing or decreasing. So it really becomes very important to assess the trends in aerosols resulting from both natural as well as anthropogenic aerosols. And the best possible parameter to assess this is aerosol optical depth, which is the measure of integrated columnar aerosols. Now, to measure this aerosol optical depth globally, we came across few of the Earth observing system satellites where each satellite has its unique features. For example, MISR is capable to analyze aerosols with 9 different angles, while MODIS is capable to measure aerosols with a huge swath width, whereas on the other hand, Calliope is able to measure the complete vertical distribution of the aerosols. As each satellite has its own advantage and disadvantage, so in this study, the highlight of this study is that we are taking all the possible available satellite data sets in this study to estimate the long-term trends in the aerosol optical depth. But before that, we have also conducted a preliminary statistical analysis with the ground truth aeronet stations, where we have taken data set from more than 10 years over 82 sites. And in addition to the satellites, which I have mentioned earlier, we have also taken the reanalysis dataset, that is MERA2 as well. And the parameters which we analyzed are the correlation coefficient, RMSE, MAE, and RMB. So this is the statistical analysis conducted to know how good our long-term trends will be. This is the statistical comparison with the Aeronet AOD between 2001 to 2020, which is around nearly 2 decadal dataset we have considered in our study. So here we can see that with the MODIS Aqua dataset, highest number of regions exist with having high correlation values over America, Africa, and Middle East region, while high RMSE and MAE values exist over South America, Africa, India, and Middle East region with MISR, Calliope, and MERA2 datasets. But overall, we could see the high correlation with all the satellite as well as reanalysis dataset. So with this confidence, now we will analyze the long-term trends due to the aerosol optical properties. But before that, this is the climatology derived from all the datasets. Here we could see more or less same features with all the datasets, which have been marked in the red color, where we could see high aerosol loading over Africa, Middle East and South Asia region. But when compared with the Aeronet, with the Miser, they have underestimated, while Calliope values has overestimated when compared with the Aeronet. But keeping this aside for now, we have taken the monthly mean AOD values to firstly analyze the region-wise linear regression trend analysis. So from this figure, we could see that there is a low sensor-to-sensor variability over regions like Eastern North America and Europe, whereas there was a huge sensor-to-sensor variability over Middle East, India and Africa region. So now to know how significant these linear trends are, we estimated their p-values as well. From this, we could see that the huge insignificant trend values exist over Middle East, India and Africa regions. So these are the same regions which are having high aerosol loading and high RMSE and MAE values, as I have discussed earlier. So now we thought to see if there is any role of background dynamics on meteorology which can influence these trend values, as aerosol is a integrated columnar value and any change in the background dynamics can influence these AOD values. So for that, we estimated multivariate regression trend analysis. The beauty of this multivariate regression trend analysis is that we can estimate the contributions of the different long-term oscillations such as quasi-binary oscillations as seen in the figure A, Enso coefficient, solar coefficient from the long-term AOD dataset. Now, as you can see from figure A, that these there exists a huge contribution from QBO, Enso and solar coefficient. So now, after eliminating these long-term oscillations from our monthly mean AOD, now we could get the actual significant trend values with the Modi's Aqua AOD dataset, which I have considered for here. So now after with this assurance, we have applied this multivariate regression trend analysis to all the datasets which I have considered in my study, including Aeronet and reanalysis. So here what we could see is that more or less similar trend values have been observed from all the dataset, which includes a decreasing trend over Eastern North America, South America, Europe, Africa and China region, while increasing trends were observed over India and South Africa region. In contradiction to the increasing trends over Indian region, we also saw decreasing trend over northwestern region of India with Modi's Terra, Calliope and Modi's Aqua satellite. Also, we could see the decreasing trend over Middle East region with the Calliope measurements as well. So with this, I'd like to summarize my findings that before evaluating the long-term trends in aerosol optical depth, we have made a detailed comparison with the ground-based Aeronet observations, where high to medium spatial correlation has been observed. On the one hand, where Miser has underestimated, while Calliope has overestimated the AOD values, region-wise linear regression trend analysis has given statistically insignificant trend values, while a decreasing trends using multivariate regression trend analysis is seen in connection with the emission control policies, reduction in forest fires, stilling of surface winds over arid region. However, over South Africa region, we could see increased trend values in comparison to the values reported earlier. So in this presentation, I have only shown the long-term trends obtained using the optical properties of aerosols. However, the main purpose behind using these multi-satellite observations in this study was to further evaluate its morphological, physical and chemical properties as well, which is the future scope of this study. So for more details, you can refer to this paper. Thank you.
Thank you, Gopika, for your nice presentation. If anybody has question, please raise your hands or unmute and talk.
There is one comment by L. Kumar Ray. What is the physical mechanism of Enso AOD linkage?
So, physical mechanism in what sense, sir?
Enso and AOD. How the Enso is able to influence the AOD? That was the question.
Actually, this Enso oscillations, like as we all know that La Nina and El Nino. So when these oscillations will happen, there's a huge variations. Like some regions will encounter these droughts, and some will encounter huge rainfall. So this background meteorology has huge influence on this AOD values as well.
Okay, nice. Thank you.
Thank you, Gopika. Yeah, we will move on to next talk. The speaker is Lakshmi NB. She is from NSES. She is going to talk on retrieval of near surface PM 2.5 over India using satellite lidar observations. Over to you, Lakshmi NB.
Yes, sir. Thank you, sir.
Please maintain time for 8 minutes.
Okay, sir. So is my screen visible?
Yes, please keep in view mode.
Okay.
Full view mode. Yeah.
Yes. So I am audible and my screen is also visible, right?
Yes, please proceed.
Yes. So good evening all, I am Lakshmi and today I am going to talk on the retrieval of near surface PM 2.5 over India using satellite LiDAR observations. So regional aerosol loading is alarmingly increasing over India and monitoring PM 2.5 is very important due to its potential impacts on changing regional climate, air quality and its effects on human health. So ambient 2.5 is the 5th ranked risk factor for global deaths, and in India, premature mortalities due to PM 2.5 exposure exceeds almost 1 million per year. Also, regarding the economic loss, it causes about more than 90,000 million US dollars in India, an economic loss of 90,000 million. And studies carried out during the COVID-19 pandemic, they have established a positive link between PM 2.5 emission and the number of positive cases over India. It demonstrates the vulnerability of people residing in highly polluted regions of India. It's their vulnerability to coronavirus infection. Moreover, the wintertime pollution over India has been associated with adverse weather conditions, such as extreme haze and fog conditions, especially over the Indo-Gangetic Plain. They lead to severe visibility degradation and issues with the road traffic and also the air traffic. Then this causes loss of life and property. So for exposure assessment studies and assessment of severe weather events, the PM 2.5 estimates near to the surface are very crucial. So usually PM 2.5 near to the surface is characterized using in situ measurements and remote sensing measurements. Satellite measurements gives large-scale long-term observations, which make it one of the best tools to study the spatial distribution as well as the long-term trend in aerosol properties. So there have been a few attempts over the India region to retrieve PM 2.5 from passive observations of AOD. But these methods usually use a linear regression method or an development of an empirical relationship between AOD and PM 2.5, which is not always constant because it depends on the aerosol vertical distribution and also the thermodynamic state of the aerosols, which vary from region to region and also from season to season over the Indian region. So spaceborne LiDAR observations provide an excellent opportunity. It is an active remote sensing method, and it provides vertically resolved observations and direct measurements of aerosol properties from near the surface. So present study uses Calliope observations, backscattering observations of Calliope, onboard Calypso satellite to retrieve the PM 2.5 concentration near to the surface using the near surface measurements of backscatter radiation. So we have followed a methodology by Toth et al. And he has used a well-established relationship between the optical properties of the aerosol to the and the conversion to the mass. So the primary factor here is the near surface aerosol extinction coefficient. So although Calliope gives accurate aerosol vertical distribution, its magnitude of its aerosol extinction coefficient is quite uncertain due to the assumptions in LiDAR ratio involved. And over South Asia, it's a very highly heterogeneous aerosol domain. So the AOD observations by the aerosol extension coefficient observation normalize the Calliope profiles to obtain the better values of aerosol extinction coefficient near to the surface. So here is the spatial distribution of average aerosol extinction coefficient within 100 to 200 kilometer above ground level, which is used in the present study. And one of the other primary factor is the conversion of optical properties to the from physical domain to the mass domain. So for that, we have to estimate the mass scattering and the absorption efficiencies. So for that, we have used the aerosol composition from the MERA and used ME calculations to simulate mass scattering and absorption efficiencies over the Indian region. So here is that we have developed the spatial distribution of mass scattering and both absorption efficiencies. And then another factor is the hygroscopic growth factor, because this is to account for the hygroscopic growth of the aerosols and its effect on the light scattering. So for that, we have used a two parameter fit equation by Malling et al. Based on the observations over the Indian region. So for that, we have we use the relative humidity observations from the ARS satellite. So here is the distribution. So all these parameters goes to equation to estimate the total particulate matter, which is the total PM. And to convert total particulate matter to PM 2.5, we have used PM 2.5 to PM 10 ratio from the CPCB measurements, the Central Pollution Board observations. And so here is the distribution of station-based distribution of ratio of PM 2.5 to PM 10 over the Indian continent. So this is the method involved in the retrieval of PM 2.5, near surface PM 2.5 over the Indian region from the spaceborne LiDAR. So here is the spatial distribution of PM 2.5 over India. So we can, as expected, we have a very large loading over the Indo-Gangetic plain, and similar large loading is also observed over the northwestern region and relatively cleaner peninsular India, even though its mean value of about 50 microgram per meter cube is greater than the national ambient air quality standards. So it is actually concerning. And looking at the long-term trends, the trend, the PM 2.5 at the surface is actually increasing over the Indo-Gangetic plain and the northwest India at a rate of 3% per year. And over the peninsular India, even though it is relatively cleaner, it is increasing at a rate of 4% per year. So what is the controlling factor of PM 2.5 at the surface? Like any other climate parameters, climate problems, it's a multi-parameter problem, and it's determined by the meteorological conditions as well as the anthropogenic emissions of the pollutants. So one of the well-recognized source of emission over the northern India during the winter during the post-monsoon is the crop residue burning by the farmers. That is, after the agricultural harvesting, they burn the crop on a large scale, and that produce severe emission of biomass aerosols. So here is the fire count from the models, and you can see that there is severe burning over the Punjab Haryana region during the October and the November. So how do these fire emissions correlate with PM 2.5 over the northern India on an interannual scale? So here is the anomaly in average near surface PM 2.5 between 2015 to 2018, except for that time period, it is more or less matching with each other. So we have actually carried out a linear regression analysis, and a correlation coefficient with PM 2.5 with fire count has been found out, and we can see that a positive correlation, statistically significant correlation, have been observed during the month of November, whereas during the month of October, the correlation is negative, and also it is not statistically very significant. So the reason for this is the increasing trend of fire counts during the November and the decreasing fire activity during the October region. And this has been implemented as a part of underwater ground policies, water policies by the government, for the preservation of the subsoil water table. Government has implemented Preservation of Subsoil Act during 2009, and this has actually shifted the entire agricultural pattern towards the November, and subsequently the burning also shifted towards the winter, and the delayed burning can actually lead to the worsening of air quality, because as the emissions are towards the winter, the lower surface temperature and the stagnant and more severe stagnant
Madam,
conditions.
Please try to complete your presentation.
Yes, sir. More. So what controls the near surface PM 2.5 meteorology or emissions? And the correlation coefficient shows that the fire count, the emission strength is playing a role here rather than the other meteorological factors. So PM 2.5 has a higher correlation with emissions compared to meteorological factors. So what is the extent of pollution caused by this crop residue burning? The spatial distribution of correlation coefficient between fire count during the November and the AOD is shown, and you can see that the statistically significant influence correlation is observed between the fire activity over the northwestern region to the the post-monsoon over the northern India extends up to peninsular India through long-range transport. The wind fields are also favorable for that, and it can contribute to continental pollution outflow over to the southern.
Madam, please come to conclusion slide. Please come to your conclusion slide.
Yes, sir, it is done. So shall I read this or? So I will tell that. Wintertime PM 2.5 is retrieved over the Indian subcontinent using near-surface backscatter observations of LiDAR from space. And the near-surface PM mass concentration during winter is increasing over the entire Indian region. Wintertime near-surface PM concentration over the Indian subcontinent shows a statistically significant correlation with post-harvest crop residue burning. Interannual variability of PM 2.5 shows higher correlation to burning emission strength than the meteorological parameters. And influence of agro residue burning over the northern India spatially extends up to the peninsular India and can contribute to continental pollution outflow. So we suggest that sustainable solutions should be implemented to agronomic practices during the month of November, especially during the month of November, to effectively reduce the far-reaching implications of this fire activities over the northern India. Thank you, sir.
Thank you, Lakshmi, for the talk.
Yeah.
We have one comment in the comment box from Kumar. Have you compared these estimated PM 2.5 trends with the in-situ PM 2.5 measurements?
Yes, we have used the CPCB data to validate this retrieved PM 2.5, and our estimates are almost 10 to 15% greater than the CPCB data. That work is under progression, so I may be able to tell more about that afterwards.
Fine. Thank you. We'll move to the next. Lakshmi Kumar.
Yes. So now we have talk by Shyam Mehta. He's from Bose Institute. So Mehta's talk is on variability and comparison of aerosol and PWV from the measurements of satellite over Darjeeling. Dr. Shyam Mehta, over to you. Are you there, Dr. Shyam Mehta? Shyam Mehta, are you there?
Shyam Mehta, are you there? I think there is no reply from him either in the chat box also.
Yeah.
I think we'll move to the next. Meanwhile, he may come.
Yes, sir. We'll go to next talk.
Yes.
Yeah. So the next talk will be on what drives the prevalence of atmospheric water-soluble organic aerosols over the tropical hill station in the Western Ghats. The speaker is D.K. Deshmukh. So Deshmukh is from SpaceX laboratory. So I request Deshmukh to proceed for his talk. Please maintain the time, Deshmukh, for 8 minutes. Yeah, please keep in full screen. Yeah, now it is perfect. Please proceed. We are unable to hear you.
Please unmute. You are already muted. Deshmukh. Deshmukh, please unmute.
Is it okay now?
Yes.
So the topic of my presentation is what drives the prevalence of atmospheric water-soluble organic aerosol over the tropical hill station in the Western Ghats. So as we know, organic aerosols have an issue of scientific studies because it is related to the global and the regional climate change and the chemistry in the atmosphere. They are a major portion of fine aerosol particles. Their primary sources are fossil combustion, burning and biogenic sources, whereas their secondary sources are the oxidation of precursor compound in the atmosphere, mainly in the gas phase and aqueous phase. So these organic aerosols can transport from the source site to the remote area, and during transport, this can transform into the atmosphere by photochemical aging and produce highly water-soluble organic aerosols. These water-soluble organic aerosols can enhance the ability of aerosol to act as CCN. So the study of water-soluble organic aerosol in remote area is usually ideal for the better understanding of their sources and of formation processes as well as their impact. So these are our target compound, dicarboxylic acid, oxocarboxylic acids, and the dicarbonyls. And this is the mechanism I proposed in my previous publications, where this can, how and from where this compound can produce in the atmosphere in aqueous phase. So as we know, Western Ghat has a region of global importance because of the conservation of the biological diversity. This region plays a significant role in modulating the monsoon rainfall because it influences the Indian monsoon. There are few studies which reported a substantial decreased trend in the rainfall and the important role of carbonaceous aerosol particle in CCN activation of aerosol particles. So the organic compounds that can alter the CCN property of atmospheric aerosol particle need to be investigated. Our sampling site is the Ponmodi, that is a tropical heat station in the Western Ghat. This Ponmodi site is about 900 meter above the mean sea level, and this is a remote site which has no any local anthropogenic sources. So we collected actually a size segregated sample in 5 different sizes using Shivata 5-stage high volume sampler on quartz fiber filter during 31st January to 21st March 2020. However, because of the enough amount of the material on the filter and because of the climate relevance, we analyzed the PM 1.1 fraction. So we analyzed these aerosol samples for this organic carbon and elemental carbon using carbon analyzer. Water soluble organic carbon was analyzed using a total organic carbon analyzer. And we newly established the advanced method for the molecular level measurement of water soluble organic compounds using GC gas chromatograph equipped with flame ionization detector using derivatization technique. So the recovery of these water soluble organic compounds is in the range of 85 to 90%, and the analytical error is about 10%. So these are the results. The total carbon concentration was on average 3.2 microgram per cubic meter. In this total carbon, we found the OC is the dominant and the EC was the minor component. So we found that the organic carbon to elemental carbon ratio of 11, which indicate the presence of the secondary organic aerosol. This is further supported by the WSOC to OC ratio that indicate about 60%, 62% of organic carbon is a water soluble organic carbon in Ponmodi samples. So these are the air mass trajectories which shows the both influence from the continental and marine sources. However, based on analyzing this bulk parameter like organic carbon and water soluble organic carbon, it is difficult to differentiate what is the sources in a formation process. So we move to the molecular level characterization of water soluble organic compounds. So these are the molecular distribution of the organic compounds we detected in the sample using gas chromatograph flame ionization detector, and we detected a series of dicarboxylic acids, oxocarboxylic acid, and dicarbonyls. So we found oxalic acid is highly abundant as compared to other compounds. So one important thing is that we found the smaller low molecular weight compounds are more abundant as compared to the high molecular weight compound, which indicate that they are a product of the photochemical chain reaction in the atmosphere. Because there are very limited study in India, we compare these levels of water soluble organic compounds of Ponmodi with other studies like Thumba and some other studies, Chennai, Nainital, and Mount Everest. We found the dicarboxylic acid concentrations in Ponmodi was lower than the Thumba, but it is higher than Chennai, Nainital, and Mount Everest, which has almost a similar type of characteristics. However, another important result is that the oxalic acid, which is highly abundant in the sample, its concentration is Ponmodi is almost comparable to Thumba, although Ponmodi is the remote site, which indicate that the Ponmodi aerosol samples contain a significant amount of water soluble organic compounds. Because we found a very high level of organic compound, we calculated the carbon concentration of those water soluble organic compounds detected in Ponmodi aerosol and estimated their contribution in total carbon and water soluble organic carbon. As literature reported, this kind of water soluble organic compounds contribute about 1 to 3% of total carbon in urban aerosol and about 10% in remote marine aerosol, that is in very, very remote marine aerosol. However, we found in Ponmodi sample, these water soluble organic compounds carbon contribute on average 9% of total carbon, and whereas it is about on average 22% of water soluble organic carbon. So these contributions indicate that the Ponmodi aerosols have a more water soluble organisms formed by oxidation of precursors compounds. So to further know what are the sources of these water-soluble organic compounds, we use the diagnostic ratios as a tracer for source identification, and we use a two kind of ratio. One is the succinic acid to malonic acid ratio. This tells about the significance of fresh aerosol versus edged aerosols, because succinic acid photooxidizes to malonic acid in the atmosphere. Our value in body sample is about 0.60, although it looks like small as compared to those value reported in the remote site where photochemical aging was very, very strong. It is almost twice higher as compared to the primary values reported for the primary emission, that is around 0.30 or 0.35. This indicates that these compounds can be come from secondary sources, but the photochemical aging of water-soluble organic aerosol formally was not strong as that seen in the remote region. Other second ratio is a phthalic acid to azelaic acid ratio. This ratio tells about the significance of anthropogenic versus biogenic sources, because phthalic acid is the tracer of anthropogenic sources and azelaic acid is the tracer of biogenic sources. These ratios, the value in per mole sample is 0.78. And even when we compare this value with the sites where very high anthropogenic influence was observed, for example, Bay of Bengal, IGP outflow samples, or Chinese samples, or Mount Everest sample where anthropogenic aerosols or biomass burning aerosols was more. Based on these results, we conclude that biogenic sources had a significant impact on the composition of water-soluble organic aerosols in polymer sites. So another piece of evidence we have that so a strong biogenic contribution on the composition of water-soluble organic aerosols, that is the relative abundance of dicarbonyls. These two dicarbonyls, glyoxal and methyl-glyoxal, is a global source of secondary organic aerosols, because glyoxal, if we see the biogenic isoprene oxidation, glyoxal come about 47%, whereas methyl-glyoxal come about 79% from this biogenic isoprene. And we estimated the relative abundance. We found the glyoxal contribute about 26% and the methyl glyoxal contribute about 74% in pulmonary sample. So this further indicate that pulmonary aerosols, mainly the water-soluble organic aerosols as pulmonary, had a significant impact of biogenic sources. So finally, based on our these results, we propose one mechanism. So where these biogenic sources, either terrestrial plants or the marine phytoplanktons, can emit biogenic volatile organic compounds like isoprene and unsaturated fatties. Those are abundantly emitted by this higher terrestrial plant or marine phytoplankton, and these compounds can oxidize either in the gas phase or aqueous phase.
Please complete your presentation.
Yes, sir. One more slide. Some intermediate compound which can further produce several kind of water-soluble organic compounds via the mechanism I proposed in previous slides. So the conclusion is that the water-soluble organic compounds we detected in pulmonary aerosols are a product of photochemical chain reactions. Although photochemical aging of organic aerosols pulmonary was not severe, pulmonary aerosol have more water-soluble organisms formed by oxidation of organic precursors. We found the biogenic sources drive the prevalence of water-soluble organic compounds as compared to anthropogenic sources at a pulmonary sites. And based on the high abundance of this water-soluble organic acids, we conclude that it can enhance the ability of aerosol to act as CCN and modify the water uptake property of aerosol particle over the tropical hill station in the Western Ghat. Thank you very much.
Thank you, Deshmukh, for your presentation. Now it is open for discussion. Anybody has doubt, please.
I think there are no comments in the comment box, but still we have some 1 or 2 minutes. Is there anybody have any comment? If not, we'll move to the next.
Yeah.
Shall we go move to the next? Yes,
sir. So we have talked now on probing the genesis of extreme BC episodes over a polluted metropolis near land-sea boundary. So the speaker is Gargi Rakshit. Gargi Rakshit is from Institute of Radio Physics and Electronics. Please, Gargi.
Hello. Actually, Gargi Rakshit has withdrawn from the meeting. Okay. This was a last-minute change. So can we move on to the next?
Okay.
Yeah. So now the talk is on variation of trace gases in Kannur town, a coastal South Indian city. The speaker is Nishant T. Nishant T is from Sri Krishna College, Guruvayur. Nishant, are you there, Nishant? Nishant, are you there? Nishant, can you hear us, Nishant? Nishant? Sir, he is also, it seems, is not there.
No, Shyam Mehta is there now?
No.
No, in this case, now we have to close this session. Should we wait for 1 or 2 minutes?
I think
LOC.
Yes, we can wait for a few minutes, or if there are any questions regarding any of the talks, maybe now there can be some discussion.
It's a good idea. If anybody have any comment or suggestion or clarifications in the already existing talks, few minutes we have.
I am allowing the mic access to everyone, so there can be a discussion.
Deshmukh, I have a question. Probably I wanted to know that. So what is the method to know this photochemical processes? How do you study these photochemical processes? Because you mentioned that PONMIDI, it is mainly because of these photochemical processes. So how do you study this photochemical process? Deshmukh is there in the room?
Okay. Yes,
Yeah.
sir. Yeah. So I know. Okay. So the photochemical process, if you want to know, first one is the actually field measurements where we can analyze some specific compounds. For example, in my presentation, I saw about the malonic acid to succinic acid ratio. That is a good ratio to say photochemical aging. So in remote site, as there are several kind of study which reported very high ratios, and in urban aerosols or where the anthropogenic aerosols or biomass burning aerosols are more, the ratios are decreased. But very fresh kind of aerosol where suppose you will suppose very near to the source region, if you will collect the sample, you will get ratio was 0.3, 0.25, 0.3 like that. This is one thing.
Are these processes are depending upon the season? Probably in
definitely
season, it is quick, or the speed of these reactions.
So it can depend on the solar radiation. It can depend upon the either it is a gas phase chemistry or aqueous phase chemistry, because sometimes aqueous phase chemistry also enhance this oxidation process, and also on the oxidants like OH radicals kind of things, or ozone, or also the precursor compound is very important. And so this is about the field measurement. Another is the laboratory measurement. People do actually nowadays to confirm really this compound is coming from that precursor or not. So there UV light irradiation method, some literature available, where they irradiate the precursor compound for suppose 1 hour, 2 hour, 3 hour. They irradiate without aqueous phase or in the presence of the aqueous phase kind of thing. So this is the two things actually to confirm that the photochemical process is there or not. Yeah.
Thank you, Deshmukh.
Yeah, thank you, sir.
Is there any clarification required on any of the talks today since afternoon 2 o'clock? If not, I think we have to close now. Over to the LOC. Before that, actually, we would like to thank all the speakers who has nicely presented the results and which of a very high quality. And I thank co-chair of the session, TV Lakshmi Kumar, for nicely handling the session. And now over to LOC.
Sir, before that, I would like to thank the chair of this session and organizing committee of the symposium for giving me this opportunity. Thank you.
Thank you. I would like to thank M. Venkatratnam for chairing the 2 sessions of the day, and TV Lakshmi Kumar for co-chairing the second session of PS1. Now I would like to request M. Venkatratnam to announce the closing of PS1 day 1 as we end day 1 of NSSS 2022 on a high note. Thank you.
Okay. Thank you very much. And very nicely, as today since morning plenary talk, and after that the session has started today. And very nice talks were there. And please, for tomorrow, we have the plenary session starting at 10 o'clock in the morning and up to 1 o'clock. And our session PS1 again starts at 2 o'clock in the afternoon. And tomorrow, Dr. Sunil Kumar, Dr. Madhavan, and Dr. Basha will be chairing the sessions. I request all the participants of this PS1 to present at least 15 minutes before the starting of 2 o'clock. Thank you very much, and let us close for today. Thank you.
Thank you all.